First of all, thank you very much for this opportunity to be here with you and to have the chance to discuss about the very, I will say, interesting topic of visual place localization. So today it will be very applicative, and you will see that this visual place localization topic can be very useful to resolve important challenges and problems in robotics and autonomous driving. And also that's, I think, very good use case to discover, like to talk about more fundamental concepts like contrastive learning, and also to go a little bit back in history and to see what are the foundations for those type of problems, especially like in image retrieval, etc., etc. But before digging directly into the technical part of this speech, I would like to tell you a bit who I am as well. I mean, I had the chance yesterday to talk with a few of you during the walk. But I would like to have the chance also to tell you a bit more. Oh, I don't know. Okay, great. So, thank you very much for the great introduction, and also like very good job for the pronunciation of my name, because that's I think a very tough one. So, as my name, or perhaps like my pronunciation might suggest to you, I'm actually originally from France, where I had the chance to meet some of the organizers of this event. So I received my PhD from a small place in France called Burgundy, which is quite famous for wine and cheese, as any other places in France, I believe. And in 2015, I took a quite important decision because I went to the other side of the planet to do my postdoc in Korea, and then I pursued my career there, which is quite, I would say, not very common. You know. So I worked for 8 years in KAIST, and very recently, like 3 months ago almost, I joined the State University of New York, actually there, Stony Brook University, more exactly, which has a branch in Korea. So they somewhat forced me to put the next slide here, okay? Just because we have to advertise that we exist, because we're a small structure. So I think like maybe some of you might know like Stony Brook or SUNY, okay, which is located in New York. But very few people know that we have actually a branch in South Korea. And well, we're quite small, but we're expanding more and more. And especially I work in the CS department, and we're looking actually for more undergrad and graduate students. So we have like different types of funding, etc. But I'm not gonna make you too bored with that today. So I would like to tell you more about what I'm doing in research and how it's connected as well to what we will actually discuss about right after that presentation. So one facet of my research is related to connected vehicles, which is a topic that I think I'm pioneering since like 2015. And here is just like a rough timeline of what I have done on this topic for the past 7 years already. So I will show you just a few of these work that were actually pretty interesting. So for instance, in 2016, with the company Bosch, we developed a system that allows you to make the car in front of you invisible. So basically, you have to imagine that those two vehicles, they have the ability to exchange any sort of data. You know, they are connected, for instance, via local network or via internet, and they are also equipped with cameras. And here the goal is like, imagine you're driving this blue car in the back, and you want to basically overtake this truck in front of you, but the visibility is not very good. And then you press a button in your car, and you have some like on the screen or on the HUD. You can basically make the truck in front of you invisible in real time. So I will show you a few. I won't go through the technical details, but I will show you some live example of it. So on the top part, this is the original view from the following car. In front, you can see another vehicle that is connected with us, and on the bottom, you can see actually that we virtually make the car in front of us invisible. And so the idea is really like if there is a pedestrian crossing in front of you, you can see through the vehicle in front of you. So well, it involves a certain number of things here, like real-time 3D reconstruction, and also a big part related to localization that we will discuss today. Here is another example because we did the technology transfer in Germany. So here it was in Hildesheim. So when we actually tested on the German vehicles. So you can see on the top right, there's the output of the system. So that was a very fun project, I would say, and our industrial partner were quite satisfied with the output, so they wanted to pursue this adventure towards something much more challenging, which was the localization of the swarm of vehicles. So we were not here limited to only 2 cars, but to basically a swarm of vehicles, like 2, 3, 10 vehicles. So here is a demo with like 3 cars connected to each other, and you can see that we can all localize them in space in real time. And we extended what we had done before, but this time to see through multiple vehicles in a row. Okay. So that's also like, if you understand everything that we will discuss today, you should be able to replicate something like this without too much trouble. And a bit more recently, I got interested more into like how the existing network of CCTV cameras could be useful in the context of connected vehicles. So here we have 2 main challenges to resolve. It's like, first, how we calibrate those CCTV cameras in the city, like without the need of like specific calibration pattern or anything. You know? And by calibration, I mean like how to localize them, like in terms of like a GPS coordinate, but also their intrinsic parameter, their elevation, and like plenty of other information. So how we auto calibrate those type of cameras. The other challenge is that now, even if your camera is calibrated, you need to extract information about the traffic, about what you're looking at, right? So also here we had to develop like new strategies basically for 3D vehicle real-time detection. And it was, I would say, a quite difficult task because there is no such data set and for this particular case. And like we had to use basically a ton of synthetic data, which transfers very badly when you try to basically apply your network for real-world data. So we have also to develop global domain adaptation strategy, etc. So here is one part of my work, but this is, I'm not limited to that actually. I do plenty of other diverse topics. Like I believe I am myself quite a guru in camera calibration. So if this is something you like, you can always come to talk to me. Like I try to calibrate camera in any possible ways, like using deep neural network, or like what if we calibrate plenty of cameras that doesn't have overlapping field of view, etc., etc. So also I have quite many works in 3D reconstruction. Actually a lot of works in the context of assisted or autonomous driving, but also more generic topics about like how you better detect key points in an image, or how we perform like indoor reconstruction using implicit representation, etc. So okay, that's a bit slow. Alright, and also plenty of other stuff related to different part, I would say, of computer vision, like domain adaptation, data set sharing, visual tracking, etc., etc. Okay, but today I want to focus more specifically on visual localization. So I will share with you the slide of this talk today. You see we'll go through actually plenty of different facets, different aspects of visual localization. And you will have access to plenty of different links, different lectures, different papers that if you want to dig a bit more into details, if you're interested, you will have access to it. Okay, so I will share all of this via Google Drive link later. I will ask the organizer basically to send you that. Right? So these are the things to be covered. I think like for the last part, we will go very quick on the part about super points, but we will see basically, we won't see like the most recent existing techniques in that field, but we will see like really like the approaches that have reshaped entirely this field and that have influenced like basically most of the paper related to visual localization. So first of all, you might wonder, what do we mean by visual localization? What's the point of that? So here is a brief definition that is actually self-explicit. It's like visual localization is the problem of estimating the 6 degrees of freedom of a camera pose, I would say, from which a given image was taken relative to a reference scene representation. So I don't know if you're very familiar with like 3D computer vision, but like when we talk, for instance, about 6 degrees of freedom, we of course mean like the 3 coordinates of the position of the camera, x, y, z, and also the 3 degrees of freedom of the rotation of the camera in the scene. Okay? So here you can see that we are mentioning about the relative pose in a reference scene representation. So what we mean by this is like, we want the pose of this camera, so the location and the orientation of this camera, with respect to a model. Okay? Any sort of model. In that case, for instance, this is a 3D model, and if I give you this image, I want to know where this picture has been acquired exactly in space. So I believe with a centimetric level of accuracy, or something like this. Only using that image and that 3D map, for instance. Okay. So we can use different type of representations. We will come to that later. But you might wonder why we want actually to do that. Actually, we already have pretty good sensor like to localize ourselves. We do the GPS, for instance. Actually, I give some lecture like to the future vehicle department at KAIST, and often the student, when I talk about like using a camera to localize basically a car, they're like, well, that's a bit useless. We have the GPS. Well, actually, the GPS in many cases this is failing. Like for instance, when you have a difficult weather condition, or when you're in an urban canyon, etc., etc., or if you have like just poor reception for satellite or a tunnel, for instance, you have many corner cases, and overall the GPS tends to lack accuracy. Like at least to develop autonomous driving, you need something much more accurate than what the GPS can provide you. Or you need to move to a DGPS, for instance, which has other type of limitation and also different costs. So using camera for localization is actually quite desirable, and that's the reason why you will see many examples that in many industries, like we tend to shift to camera, not entirely, but often like as a complementary source of information for localization. And this is desirable for many reasons, because this is low power, and this is not like a LiDAR, for instance, that require to send some laser in the scene. So this is also very compact and widely available, quite cheap. And also, images contain not only information for localization, but also like plenty of other like semantic level information. Or you can basically use your camera for different purposes. Okay. One other practical aspect is that it's working perfectly indoor, which is not the case of GPS, for instance. So I was speaking about, when we speak about localization, as we mentioned before, is localization with respect to something always, okay? Like, it can be, for instance, if you think about a real scenario for yourself, like if you need to travel in a city, you will try to localize yourself in a map of the city, for instance. You walk in Kathmandu and like you look the name of the street, and you will try to figure out where you're located in that city, okay? When we talk about visual localization, we often use different type of representations, like 3D point cloud, okay, like only basically a set of XYZ coordinate that will represent the scene, or a 3D map from structure for motion. So many people are quite confused with the difference actually between both. Like I would say that the 3D map from structure for motion is much richer than what the 3D point cloud can give you. For instance, the 3D point cloud acquired with LiDAR was just a bunch of 3D points. But if you think about the 3D reconstruction from structure for motion, you basically have the position of the 3D points of the scene, but you also have the local descriptor that has been used to match the points and to triangulate them. You have the coordinate and the position of the cameras that have basically built this model. You have actually much more information. And often when we do visual localization, we take advantage of like all those extra, I would say, metadata that we have access to. So it's not limited only to that. You can also do visual localization using the blueprint of a building, or using like a CAD model that you have beforehand. And it can be many more things than this. It can be, for instance, some implicit representation, like nerve, for instance, that you can use to localize the camera inside. So I will actually give you an example, like at the end of this talk, about like roadmap-based localization as well. So using camera, how we can basically localize in such type of very specific representation. So we have seen like what sort of model we can use to localize ourselves, and now we can also discuss about what sort of images we can use to localize ourselves inside of those maps. So most of the time, like the technique we discussed today, they will mostly be designed for perspective cameras only, because they're like the most common ones that we can have. So just normal plain camera that you might have in your smartphone. But there are also other modalities that can be interesting. Like for instance, using omnidirectional images to localize yourself has a certain number of advantages. Like here you will see like a much wider portion of the scene, or the entire scene actually, and it can give you much more clues to localize yourself. So that's also something quite desirable in that context. We can use also different type of modality like thermal imaging, okay, which would give you some advantages to localize yourself in night condition, or using stereo vision system, from which you can get some I will say, structure information of the scene that can be crucial to improve the localization accuracy that you may have. So, and also you can work on video. For instance, this is typically what we do to improve the robustness of localization. So there are actually, like here, you can just be image native and try to localize yourself with any sort of visual data you can. And by extension as well, it's maybe a bit of an abuse of language, but we can also consider LiDAR localization as a visual localization technique. So there are different granularities in for visual localization, I would say. So, and we will discuss about both of them today. The first one is visual place localization, or in different contexts that can be called image retrieval. It's actually a very simple problem to grasp. Is that imagine you have a huge data set. So imagine you collected like I don't know, like 10,000, 1 million images in Paris, and you have a geo tag for each of them. You know those exit 5, for instance, like they can provide you with the GPS position of each of those images individually. Okay? So you have this collection of images, and now you come somewhere in Paris and you take a picture of one building, and you wonder, like, where am I located? So what you can do is you can try to find the most similar images between the current image and one image in your database, and to retrieve it and to look at this GPS position, and then you can say, well, actually, my current image here might be actually acquired nearby this place where this retrieved image has been captured. Okay? So that's one way. The problem with that strategy is that it doesn't really resolve the problem I told you in the first place. It doesn't give you the exact position of the camera. It just gives you basically a rough approximation where this image is maybe has been acquired. Okay? But what we want is something much more accurate than this. Like, again, actually something that can be like accurate up to a meter or centimeter even. So what we call visual localization, at least the real definition of this term, is really when you start from one picture and one basically representation like a 3D map, and that you will try to solve the entire 6 degrees of freedom problem localization. Okay, so we will actually see both of them, and we'll see like the difference that you may have. Okay, so like quite recently, I would say we started to try to resolve that problem using deep learning. Okay, so that's basically that's what we do in pretty much any strata of computer vision these days. And there are two, I would say, major architecture to address that problem. One of them is a direct post regression that we'll see today, and actually it will be the topic of the lab of today. The idea is like, given an image, you will use a deep neural network to basically estimate the 6 degrees of freedom of the camera pose in your reference, in your map, or in your set of images. And the advantage of this is that this is very fast, and we'll discover that it doesn't scale very well for very large environment. So we will see actually all those limitations. And on the other hand, you also have the image retrieval, which is basically you have a large data set of images, and for all of those images in your data set, you will extract a representative descriptor for each of them, like a vector, that basically will tell you what this image contains somehow, and you will create basically a huge database of them. And the goal of the game here is like, given a query image, you will also extract one descriptor, and you will try to find the nearest neighbor in that database, such that you can have a rough approximation of the pose of your camera. So again, here it doesn't give you the 6 degrees of freedom pose of your camera, but it will give you an approximation. So those two approaches actually can be not entirely independent. We'll see later that they can be complementary. You can use them like together, and they're actually a pretty good match if you want to have like a fast and accurate localization of your camera. So first we will see, before like looking into the details of that, we'll see what application it can help you to resolve, okay, to address. So the first one is actually what we have seen before, the Rameau visual localization by image retrieval strategy. Actually there is a website for this. So you can basically provide one image of a city, okay, and it will look in his database which one of the images he has in his database, or like similar to the one you provided. Okay, so for instance, I provided this image, and it retrieved actually this set of images that looks quite similar, and it will tell me where all those images are located given their GPS coordinates. So if you average actually, for instance, the top 100 most similar images, you can have a fairly, I would say, accurate estimate of where the image you provided has been acquired. So that can be one very simple application for outdoor, but I would say that where this technology takes all its importance, this is when you try to resolve this problem inside. Okay, so there are plenty of industries that can benefit from such type of localization strategy. Like for instance, in retail or airport, I don't know if, for instance, you visit the Incheon airport, there are tons of robots moving around, and they are being localized, like using not only camera but also LiDAR actually. It can be used for universities, stadium, or whatever. There are actually plenty of possibilities where you can use localization. Here is an example from Google a couple of years ago, and I believe they have actually a much better technology nowadays, where you can see that they will localize the camera in real time in a building, for instance. So you can see all those key points here are matched with respect to the 3D map, and then they can estimate very accurately the pose of the camera moving around this complex. So here is actually work from some friend of mine from Neighbor, so Neighbor Korea and Neighbor Europe, where they pushed the challenge a little bit further, because they tested basically in more complex scenarios where you have plenty of people moving around in the metro of Seoul. So like from a hand-on camera, so that was actually also a very good job here to help people navigate in the underground of the metro. So I have actually collaborated with them on this. So this is also a very nice illustration of what you can do with visual localization. So here, okay, you can also work on mixed reality. So wait a minute. Oh, I cannot skip. I wanted to see some part of it, but okay. Okay, anyway, that's quite obvious that you can also apply it, for instance, to metaverse application or whatever related to distant working. You know, if you have plenty of people wearing, for instance, some Oculus, you know, and you want to share a common workspace, also we apply localization quite extensively on that. Also, this is used a lot for vehicular localization, okay, where we have to address here a certain number of challenges, like a vehicle will typically drive over any time of the day or the night, so you need still to be able to localize the vehicle. The heavy traffic can be a difficulty. We also have the change in the seasons, etc., etc. We'll come back actually later to the challenges posed in the context of visual localization. So, however, the advantage when you try to localize a vehicle is that you have plenty of clues from the environment, like the road markings. Again, I will give you a certain number of personal examples here. You can use the road sign to localize yourself, the curbs, or the shop sign, for instance. So, somewhat it can simplify the problem quite a lot by using those type of clues. So, I will show you, for instance, an example where we try to localize a vehicle based on the detection of road markings. So here is a work I have done quite some time ago. After I will show you a more recent work. So we basically developed a quite robust road markings detector that we apply to localize ourselves in the road. Basically what we try to do here is to create a map of road markings. Okay, so we use a visual slam system and we triangulate the position in space of each road markings, and we use the succession of the different road marks to localize our vehicle, and we ended up with something fairly robust actually, but you will see later something a bit more advanced regarding those type of strategy. So here is just an example of the query and retrieve images. It doesn't matter. And also, yeah, I see few things. And okay. Also we can use maps to localize ourselves. Okay? For instance, if I give you a map of the city, there are some very clever strategies that have been developed. Okay. Okay, for some reason I cannot navigate through the video, but that's okay. You will see more example later. Okay. We'll come back to vehicle a bit later in the presentation, so this is fine. Also, visual localization is very commonly used if you work a bit in SLAM. So if you're not familiar with SLAM, the idea here is given some video sequence from a camera, is to build a real-time reconstruction of the environment. The problem with those strategies is that they tend to drift over time, okay, because you will accumulate a little bit of error. You know, like this is the case here, for instance. Okay, so we moved a lot along a certain path, and we actually end up somewhere where we're not supposed to be because we drifted. And using visual localization, we can try to see if this place has already been visited before, and we can estimate, given some correspondences, how much we have drifted over time, and we can basically redistribute this error over the entire loop, and basically resolve that problem of drift in that sense. Okay, here is like an example, like from the typical Kitty dataset that's using RVSLAM or RVSLAM2 in that case. So you can see that we use like local key points to build sparse reconstruction of the environment. And at some point, this car will come back to a place it has already visited, but it has accumulated a certain drift. And you will see that thanks to place localization, we're able to not only determine that we have visited this place, but we can also calculate the accumulated drift and correct it later. So here it will come back to a place it has already visited in a minute, like here, and then it will adjust the map accordingly. So, well, that's actually a very useful thing to do place localization, but this is not necessarily an easy one. Okay, so for instance, you will very quickly realize that there are plenty of different challenges you have to address. Like if you want to develop a place localization problem, you want it to be robust to illumination changes. Because if, for instance, you have a database of images, or if you have trained a model to work only in good illumination condition, day condition, for instance, and all of a sudden you try to localize yourself in the night, then likely it's not going to work. So you want a system that is like robust to those type of scenarios. So that's one of the difficulty. Another one that is extremely common, this is the problem of low texture and repetitive pattern. Like typically in indoor environment, that's probably one of the most difficult scenarios. Like those type of corridors where you have like no texture to localize yourself. Even for a human, actually, it can be a sort of maze, okay, to know where you are when you go to those type of office or companies. The other problem is, for instance, a repetitive pattern that can easily complexify your localization. Typically, if you see those repetitive like structure on the sofa, it can confuse a lot your localization strategy and give you actually the wrong position for your camera. So also another one that is very common, this is the strong viewpoint difference between the images you have in your training set, for instance, and the query image you try to localize. For instance, on the top row here, like those two images are acquired in the same workspace, except that this one is much closer to this window, and you can see that you have like this difference in scale, like leads to drastical change in appearance in the image. So this is a challenge. So something I would say even more complicated is when you have like opposite viewpoints, like completely like here, for instance. Like this image is actually acquired from this direction here, and here it's much more complicated to basically figure out it's actually from the same place. So you will see later that people actually try to use some semantic information of the scene to somewhat like resolve those problems, but here it's like particularly difficult. Okay, I already mentioned about day and night, and about segmentation. You have also seasonal changes that can be a problem, like if you basically like have only a database that you acquire during like summer, and all of a sudden like you try to localize yourself in autumn, this is likely that you will have difficulty to localize yourself. And another very common scenario, at least in urban environment, is like all the occlusions caused by other objects, like vehicles, etc., that will like make it much more difficult to know where you're located, because all your landmarks can be basically masked by those occluders. So this is, the mean won't be representative of that. So what we do, we compute the percentage of image that will pass a certain number of thresholds, like for, like, I would say different level of difficulty. For instance, if your image is localized with, let's say, less than 5 meters error and less than 10 degrees of error, then it will pass basically this test of low accuracy. Okay? So it means that your image will be localized in that scenario. And we have the same for medium difficulty and high difficulty. So for instance, if we look in this data set, Aken Day and Night that I mentioned before, the top score for this one, we basically perform in 90% of the case in a hard condition, it will be able to localize the camera, like here in daytime. And you can see that for nighttime as well, this is performing relatively well with a high level of accuracy. So that's the metric we use, and that's the metric you will actually replicate during the lab. So now we'll see actually, we have seen a little bit like what we can do with those strategies, and we have seen also like how we measure the error for camera localization. Now I would like to basically like introduce one of the quite old but very influential techniques in that field, which is like direct deep learning pose regression, and in particular one of the first techniques in that field, which was called PoseNet. It's an old paper, as I mentioned, like in 2015, and back in the day it was actually quite new. I know that now that you have all this knowledge about CNN, etc., you won't be very surprised by any like architecture or loss that has been actually used in that system. That's a very simple one, and I think that's a very good introduction to understand and to learn about visual localization. So here is, for instance, just to illustrate a bit what they were doing, a video from the author of this paper. So basically, they given an image, they're able, using a network, to directly regress the pose of the camera. Here, they use a 3D map only for illustration, okay? But in reality, they only use that image to estimate the 6 degrees of freedom of pose of this camera in space. So we'll see a bit now how all of this is working. So yes, this paper addressed the problem of relocalization, and for this, they basically developed end-to-end convolutional neural network training to regress the orientation and position of the camera. And one of the advantages of their technique, at least back in the day what they were selling, is that this is working very fast. Okay? And it's quite simple to understand the idea behind this type of strategy. So simply, I provide an image to my network, and so I don't do any classification, I will do regression of basically the 6 degrees of freedom of my camera. So it's not going to be necessarily 6 outputs, 3 for translation and 3 for rotation. We will use different representation for rotation. We'll talk a bit about quaternion. But anyway, the idea is just that. You have one CNN, you regress basically the pose of your camera. But how can we actually do something like this? Okay? How do you train that? Okay? In terms of architecture, there is absolutely nothing here. So to train the network, it needs basically a set of image and pose pair. Okay? And to get that, we can basically use structure from motion strategy to basically know the position for each images in space in a given referential. So imagine, for instance, we want to map this entire school, so we can take like plenty of pictures of the school, okay, using your phone, for instance, and we can use all those images in a structure from motion pipeline like whole map. And we have this reconstruction like here, okay? And maybe tomorrow, one of your friends is visiting the school here and takes a picture, and the question is, where is this picture located? And thankfully, using the database you have constructed, we can train the neural network to basically try to learn how to relocalize those cameras. So, yeah, we can basically capture all those images, make the true reconstruction, and the pose of the cameras, and we can basically separate certain images for testing and others basically for training. So now that we know that we can obtain basically the ground truth pose for certain of those images, we can simply train this network that will regress all the components for translation and rotation. But of course, we can use different representation that we want to regress. So for translation, inclination, it's always going to be only 3 components. But for rotation, we can use, for instance, the entire rotation matrix, which is a 3 by 3 matrix. But it will not necessarily be the most easiest things to regress. First, because this is over-parameterized in some sense, and you will have to enforce the orthogonality of that matrix. Or you can use like more compact representation, like n-galaxies representation, or like quaternion representation, which is actually used in this paper. And after actually like the PostNet paper, many of our people developed their own, I would say, rotational loss here. So here is the original architecture of PostNet, which is not that interesting to study because you can actually do it with any CNN you want. And this is what we'll do as well in the lab. So back in the day, one network that was trendy was the Google Net, which is somehow like inspired by some sort of ensemble technique where you will have multiple outputs like at different stages of your network, basically. And the only thing, so originally this network was designed for a classification problem because that's basically all we were doing back in the day, you know, in 2015. And the only thing they had to modify to transform this network into their PostNet network is to kick out all the softmax classifier and to basically simply put some fully convolutional networks that will regress your basically 7-element vector that will represent your post. So one of the novelty of this paper, or something that claimed that was very important, is transfer learning in that case. It's like they demonstrated that if you try to train like a PostNet network like from scratch, it's not working very well. This is actually very unlikely to converge to a proper solution. You can see, for instance, this blue one was basically trained from scratch, but if you use a pre-trained network from ImageNet that you will try to fine-tune, then you will have actually a way faster and better convergence of your network. And I know that nowadays this is extremely obvious to say that, but back in the day it was like more or less the beginning of those type of transfer learning strategy. So he also had a lot of influence for future work like in that field. And also show that like if you use a pre-trained model on ImageNet, this is working much better. But if you retrain it again on a place localization problem, and you basically use this model to retrain again on another place localization problem, then it's going to converge even faster and better. So they also claim that as a novelty back in the day. Okay, so here is basically the loss function that they use. So they have like the ground truth translation and rotation of the camera in space, and they basically have, I would say, this is a single loss, but they compute individually the translation and the rotation. But you can see that they use also a balancing term here, beta in the middle, that back in the day was set manually. And this beta was very problematic because it's completely scene dependent. So why actually we need that is because often the translation error will be much larger than the rotation error. Because here you can see we use a unit quaternion. So it means that the maximum error you get here is 1. But for translation, maybe your scene can be like super big. And the metric error of your camera can be, let's say, 1,000 meters. You know, it's not scaled in any way. So you need basically this parameter to adjust it to be sure that your loss is not going to be biased toward rotation or translation. Okay? So you have to carefully set this guy to be sure that they're well balanced. So it was one of the major limitations of this strategy. But after they came with basically another paper where they basically proposed to also put this parameter as a learnable parameter, and which like improved quite a lot the applicability of these type of techniques. And here is the result basically they displayed in this original paper. And so it was quite impressive at this time, because it was working like in pretty much any conditions. Okay? So the accuracy of the localization was not very great, not very accurate, but it was actually very robust to textureless environment. So something very simple, very fast. Okay? But you will see later that it posed overpriced. So here And it was, I believe, the first attempt to use deep learning for pose regression. Okay. So there were, after this work, a lot of attempts. I'm pretty sure there were like at least 100 or multiple hundreds of work that got very strongly inspired by PoseNet, like Pose LSTM, Hourglass Pose, and so many actually. So yeah, if you understand the concept of PoseNet, basically it will help you to understand plenty of our paper resulting out from this. So, like, is it as good as they advertised in the first place? Well, actually, as I mentioned, this is very robust, but not very accurate. And there is actually a more pressing and important problem than this. It's, yeah, this beta parameter was an issue, but again, that they resolved after. That was scene dependent, but mostly it was not very scalable. Like here, you have to keep in mind that you will train your network for a specific scene. So for instance, I mentioned that you can train a network like to localize yourself, for instance, in that school, but it means that this network can only be used to localize yourself here. If now you use the same network to localize yourself in other places in Kathmandu, you need to retake a new data set and to basically retrain a new network again. So this is like not something you can scale to very, I would say, large environments. Okay, you need always to retrain again and again. That costs money, that costs time. So this is definitely a problematic issue. So a somewhat a solution to those type of problems is to use some image retrieval techniques, which are much more scalable, something you can use like in much larger condition, like much larger scene. So the idea of image retrieval in the context of place localization is very simple to understand. Is imaging, for instance, you have a data set of plenty of geolocalized images in a city. You just basically try to retrieve your query image in like among those images in your data set to localize yourself. Okay, that's what I mentioned at the beginning of this talk. And to do this, just to give you like a high-level understanding of that, is that what you want to do is for each image in your database, you want to extract some descriptor from those images. So here you don't need necessarily to think that the image is the feature extractor is necessarily a deep learning thing. It can be anything. You know, like you can assume, for instance, you compute the histogram, like the color histogram of the image. Now, of course, it's not going to be robust enough, but it can be any type of feature. It can be the gradient of the image, anything that basically will give you a global representation of those images. Okay, a compact way somehow to summarize this image in a single representative vector, for instance, that you can set in that you can put in a descriptor space or a latent space. Okay. So you will do it for every single image in your database. Okay, so for instance, you take another image, you extract the feature descriptor, okay, and you save it somewhere. Okay, you know where it's located in the latent space, and you do it again and again for every single image in your database. Okay, one more and one more. Okay, so you do it for all of them. And in the end, you will take your query image and you will use the exact same feature extractor that will give you basically the position of your image in this latent space. And now to retrieve the closest image is very simple. You can simply look for the nearest neighbor. And you're like, well, actually, this orange picture was the closest one, given actually at least this feature extractor representation. Okay? And then you can know that those two images are the most similar. So that's the overall idea of this strategy. So, well, to do that as well, you can use some nearest neighbor technique. I'm not going to go into details, but I will give you the slide to give you a recap on that if you're not very familiar with those techniques. So I was telling you about like the feature extractor strategy to basically summarize your image. And I would say that one of the first and the most common that is used is the map of war strategy. That's a very old technique that is still used widely today. Actually, especially if you do a bit of SLAM, this is still what is like under the hood of most of even recent SLAM techniques. Okay? So a map of world representation can be used to basically extract the global descriptor of an image in the context of computer vision. So here there is always like a cryptic definition from Wikipedia. You don't need to spend your time on this. You can come back to that later, and you should be able to understand basically what it means. But the overall idea is that of bag of words is you will extract basically some local descriptor on an image, okay, and you will basically try to see how much those features they will come. Okay, like you will use local feature, and you will look in the dictionary of feature you have made before. We'll come back to that. To basically describe the appearance of the image. For instance, this cat, you will maybe extract that, okay, it has different specific eyes and like a nose, etc., etc., and this is what makes it a cat. So, like as the name might suggest to you, bag of words here has been originally developed in the context of NLP to characterize like what type of text, for instance, you're looking at. Okay? So the idea is fairly simple in NLP and also in computer vision. So you can see that you will start with a dictionary. And so you can think of a usual like English dictionary, for instance, or in that case we have a smaller dictionary. So imagine our dictionary is only composed of those words. 1, 2, 3, 4, 5, 6, 7, 8 words. Okay? And now given your a sentence, you will try to count the number of occurrence of each word. So for instance, in this sentence, the dog is on the table. You can see that dog is actually appearing once, is appearing once as well, etc. So you will count each occurrences of the word, and it can help you to characterize like what is basically the context of that sentence or the context of a book, for instance. So imagine if you have like a theological book, like for instance the Bible, like, and you count the number of different words inside. Maybe the word God will appear plenty of time, or the God of Jesus will appear, the name of Jesus will appear like hundreds of times as well. Okay? So this is more likely in that case that this book belongs to like something that is theological, okay? Like about religion. But if you have like a magazine about soccer, maybe ball or like players or a game will come much more often, and then it will be easier for you to basically categorize it as a sport magazine, for instance. The way it works in vision is slightly different. Like we cannot really have a dictionary of word here. So what you will build instead, this is a dictionary of feature, or like here we have patches, but in reality we will use like local descriptors of an image, okay? And we'll build a dictionary about that. We'll see how later, okay? And after a given image, what you will try to do is to extract local patches and to see to what basically words in your code book they correspond to, okay? And you will count them. For instance, in that case, the word, I would say, or the feature skin will appear much more often than, for instance, the feature that belongs to a bike. Okay, so this image is more likely to belong to a person. Okay? So the same goes for the bike, or for instance, for an instrument. Okay, so you count the number of times, basically, like certain like feature will appear in your image or in your object. So the way you will build a dictionary of feature, because again, like you don't have this readily available, right? This is not like language. So what you will do is you will collect plenty of images that you can scrap from anywhere online, and the first thing you will do, on all those images, you will extract some local key points, and you will basically run some local descriptors, whichever you want, like for instance, SIFT descriptor, from all those key points, and you will put all of them in their latent space, okay, their descriptor space, basically. Okay? And now what you can do is that you can cluster them, for instance, using K-bin. You can say, well, I want to basically cluster all those features in 10 different clusters, and now all those different clusters will represent the word, because like all those points in the latent space they are nearby, so they might have some similarity between each other. Okay? And here is like basically the way that you will build your dictionary. Okay? But here, of course, this is very schematic. The real way we do that is that we start first by capturing like all our SIFT descriptor from a large data set. So you can assume that you start with all the descriptor you have, and you will run first basically a k-min to divide the space in in actually k different clusters. So often what we do is k equal to 3, but it can be anything else. Okay? So we will basically divide it in 3 different clusters, where here you can see this is the mean for each of those clusters. Okay? So we start with the entire space, with our entire features, and we basically cluster them in 3 different distinct parts. Okay? And after, what you will do is like you will repeat this operation for each of those subclusters, and you will create basically 3 new subclusters of that part. Okay? And you will keep going on and on until you reach a certain condition, like for instance, until this leaf contains, for instance, only 10 or 5 features. Okay? But keep in mind that here we're talking about millions of local descriptors. So the tree can be very deep and very big. And actually, if we do that, is to basically make it much faster to retrieve a word in your dictionary. Okay, so for instance, if you have, let's say, like a query feature that appears in that place of your tree, then you can simply like go all along your tree, or maybe here. You can go all along your tree and to basically find to what word this query feature corresponds to. Okay. So after, when you want to represent an image using bag of words, the only thing you need to do is first extract some features in your image, some local descriptor, and you need to look basically in your feature dictionary to what words they belong to. Okay? So, and you will count the number of occurrences for each of those words. So if you're, for instance, in an urban environment, it is likely that you will have some words that will belong to, I don't know, like some feature coming from cars or from trees, for instance. So you can build basically an histogram of those words that appears inside of your image. And the number of times you have similar features that will appear in your image will be a representative of the scene you're looking at, basically. And after, you can compute the distance between like 2 of those histograms to know if you're looking at 2 similar images, for instance. So we can, for instance, compute the L2 norm between 2 word histograms from 2 different images to know if they're similar. The problem with that is that it can take basically a lot of time. So if the database becomes very large, and imagine you extract 1 bag of word descriptor for each of those images, and if you want to retrieve like one of your images in this database, it can take very lot of time. Maybe you need to compute the distance between all those descriptors. Okay, but in that case, like bag of word has one very strong advantage, and that's the reason why this is still used, even though there are much better deep learning strategy to address that problem, is that you can have the trick of the inverse index mapping. So here the strategy is quite smart, is that when you build your data set, you will basically, so here when I write keyf, it's a keyframe, okay? So what you will do when you create your data set, you will have your dictionary word that you have created before. So here we have only 7 words in our dictionary, but again, it can be millions of them. Okay? And what you will do is, like for each word, you will list like in what index of what frame this word has appeared before. Okay? So you will have basically all these indexing that you create. And now if you have one query frame that you want to retrieve in that data set, you can simply look at the first word that appeared, for instance, word 1, and you will look like in whatever frame in your database this word has appeared. And you will do basically +1 for each of those frames that share a similar word. And you will keep doing that for the other words that are like basically appearing in that query frame. So for instance, the word number 3 appears in your database for the key frame 2, 4, 7, and 9. So you will do an increment of +1 on each of them. And you will keep going for every single word, and basically the key frame which has the more word in common with your query frame is the one that is likely basically to be a good match with your query frame. So here it was for bag of word, but like later, like this strategy has been improved in many ways, and especially one that was also very influential is BLAD. And you will count like you will look in what word they're assigned to, and you will basically build a histogram of this. So there is quite a lot of quantization that goes through that print that problem. Okay. So you can imagine, for instance, that a word that appears here in that cluster, or a word that will appear here in that cluster, can still be very different. Okay. So it's not because they belong to the same cluster that they are necessarily very similar. Okay. And this is where Vlad is coming into place, is that instead of this simple, like, I would say, histogram building, here we will compute what we call a residual vector for each word in your dictionary. For instance, imagine you have 3 features that belongs to the word to for a given image, for instance. Instead of simply counting, well, this word appeared 3 times, I will basically sum like all the vectors in the referential of this word to, as you can see here. And we will basically consider the resulting residual vector as basically a representation of that word for that image. Okay, so it gives you basically a more fine-grained information, more discriminative information for that particular word that is appearing in your image. So the only problem with that actually is that before we bug a word, so we ended up with only one vector, which is like a huge histogram of length k, where k is the length of your dictionary. Okay. But at least it was relatively compact in some sense. Like you also have to keep in mind that like this k, your dictionary can be extremely big. It can be actually a vector of 1 million images. So most of the time we just like don't consider like the word that doesn't appear in your image, for instance. So it's much more compact than this already. But the problem with that is that now you don't have only like k vector of length k. Now you have like a vector of the size of your space, for instance, 128, the size of your latent space. So in that case here, is for sift, by k, which is basically the number of words in your dictionary. So this is a bit more bulky, a bit less compact than bag of words but this is also much more discriminated. So like all those strategies that I mentioned like before image retrieval, they're not based on deep learning, basically. So like at the beginning of the deep learning era, like around 2015, obviously people saw some great interest of using that as basically a good representation for an image. So the first attempt that was tried is like, what if we use basically a network pre-trained on ImageNet, and we take like, let's say the last layer as the representation for that image, okay? Or like even they were just removing the softmax and they were taking the resulting vector of this as a representation for the image, and they were simply trying to build their database in that manner and to use the nearest neighbor search to localize like a query image in this database of the database they were creating. So it was actually not effective at all in that sense, like without any sort of retraining. Nonetheless, like plenty of attempts have been done, like especially for instance this one where a bit smart strategy I would say, where they basically cut an image in small batches and they were basically taking the last convolutional layer and they were like applying like same thing as what we were actually doing for bag of words here. They were taking all those descriptors, they were building a dictionary using like k-min, and they were using this for localization. But still that was relatively unsuccessful, I would say. So they came up with like different techniques, because at this point we didn't really know how we can retrain those networks for localization. So they were like only relying on pre-trained network on ImageNet. So as I mentioned, they were just taking basically the last feature, like right before the softmax, as the representative vector, which is not very effective. So people developed some different normalization strategies and like whitening techniques, basically to improve those type of strategy. And indeed, it was helping a lot to use those representation for image retrieval. So after that, like they realized that probably this is not necessarily very useful to basically use this representation in the fully convolutional layer, but but simply to use the output of the convolutional layer and to basically apply like different different pooling on this to obtain a representative vector of that. So the initial attempt were actually by using some basic average or some pooling. So basically for each channel we were taking the maximum or the average over the channel to basically build this representative vector. But we realized later that having some generalized mean pooling, this is also something that has been like used many times in the literature in that context to basically improve the localization strategy. So in that case, the generalized mean pooling, this is actually not an average pooling, not a match pooling, but something more or less, I would say, in the middle, where you have some learning parameter that will decide how you compute like the statistics, I would say, on each different channel. So, like inspired by those techniques, like we can see that all those strategies, which are not retrained specifically for image retrieval, were actually not very effective. And this is in that context that a strategy called NetVLAD came out. So NetVLAD, also this is relatively like not a new strategy, but it's a very influential one, and this is still something that is on the top of most of the ranking in most of the ranking in the benchmark for visual localization. So the idea of like NetVLAD is to closely mimic the strategy of VLAD that we have seen before, but using a neural network. And it was a quite big challenge because the difficulty here is that it's very difficult to backpropagate like for that type of problem. It's very difficult to differentiate like this process. So they use basically for a strategy to be able to replicate VLAD but using neural network in an end-to-end manner, like especially soft assignment and contrastive learning that we'll discuss now. So here is basically the pipeline of NetVLAD. So first you have your image and then a convolutional neural network. So on the bottom here, this is NetVLAD, and on the top this is basically the original VLAD strategy. So in the VLAD strategy we extract some seed descriptor, which is not the case for NetVLAD, where we'll extract everything through a neural network. And then we have a NetVLAD layer, okay, that is composed of those different elements that we will discuss, instead of doing the aggregation that has been developed for VLAD, where we compute those residual vectors. Okay. Instead, here they will use basically another strategy, and you will hopefully understand why. So first we can like go back very briefly to what bag of words is actually doing and put some equations to it. So you can see that the bag of words, the way it will build basically their descriptor is simply with some hard assignment. Basically you have a function like here written AK will simply tell you 1 if the word exists in your image, or 0 if the word doesn't basically exist in your image, and you will count how many times a word will appear in your image, like every time. Okay, so this is what we call a hard assignment. Okay. So in contrast to that, we have seen that NetVLAD is basically computing not only the hard assignment, but also the residual vector with respect to the center of the cluster CK. Okay, so here the result of this is not just a count again, this is really like a vector that will start from the center of each of your cluster, which is basically much more representative. Okay? So the difficulty here is that if you want to do that using a neural network, is that this hard assignment here is absolutely not differentiable. Okay? So they have to basically replace this with a soft assignment that basically will consider the distance of your query point with each cluster, each center of each cluster in your vocabulary. So the idea is to be able to use it instead of the hard assignment. So here it was one of the tricks they have used, basically. So they start with a pre-trained VG16 back in the day to basically work as a feature extractor. And then after they basically do this soft assignment, here is the soft max. Yeah, okay, the soft assignment, of course, we use the soft max in that condition. Okay, yeah. So here is the soft assignment that we mentioned before, to replace basically the hard assignment that we see. So the advantage here is that basically before in the original Vlad, like everything was represented with like those, I would say, learnable parameters that you learn from your data set, which is the sum per each of your cluster in your basically tree. But here you don't really need to build that because the network will learn this thing automatically along with basically the weight of the network and the bias here to extract the feature from the image. Okay, so now using this trick of soft assignment, you can like directly build your dictionary in an end-to-end manner, plus the descriptor, which will be more specific to address that problem. So yeah. Okay, and after you can simply like, now since this part here is basically a soft assignment, and here you know that this is also something that can be completely differentiable, then you can basically replicate this Vlad vector in an end-to-end manner. Okay. So well, at this point you were able somehow to backpropagate through that network. But the problem is like how you can have a database of image to train this type of strategy. Because back in the day they didn't have access to like a large database with annotated image of different places. The only thing they had access to it was the Street View time machine, which will basically give you some GPS position of some images, okay? But it's not guaranteed. Well, and actually this is actually a pretty good type of database because you can have images which are acquired at different time of the day and at different seasons, which address like all the challenges we mentioned before. And that's exactly what we want to train those type of network because we want a network that is invariant to those type of variation. Okay. So that's a great thing, and we don't really have any strict annotation for this. The only thing we have is basically the GPS position of all of those images. Okay. So the thing is like it's easy if you have like a bunch of images where their GPS position to build to know like basically the strong negative samples, okay, like the one that are very far away, you know that they won't correspond to your query image. Like for instance, if this image is located 1 kilometer away from your query image, you know that it cannot correspond to this one, okay? But where it becomes more complicated is like to find the positive samples, okay? Because the GPS itself is not enough to tell you if an image basically has any correspondence or correspond to the exact same place as the query image, for instance. Like you can see in that case that very next to your query image, you have like this red triangle that corresponds to another acquisition of an image. It's very close, but the photographer, for instance, is looking in completely opposite direction. Okay, so this is not actually corresponding to the same place. You don't want to confuse your network, like given images without any overlapping. Okay, so you really want to find the real positive sample and to basically find a way to avoid using those like images which are close in GPS position, but which share actually like zero correspondence or zero overlapping with your query image. So at this time they were using the Tokyo Time Machine dataset, which is basically close to what I described before. So with plenty of photographs taken at various times, etc., but also with the frame I described before. And so before we go directly in the training of this, I would like to discuss a bit about the frame of similarity learning, and you will see how it applies in basically that context. So, just as an introduction of that problem, so we'll come back after to the frame of image material, but here we will discuss about like another, I would say, use case. Okay. So imagine you work in a big corporation and your boss asks you to make a security system to open the door automatically using a camera. Okay. So how can you basically address that problem? So like what you can do, for instance, is you can collect a data set of all the employees in your corporation, in your company. Okay, like let's say you have like a couple of images for each of them. And how will you address that problem? Okay. So maybe the thing you can do, you can can basically so take all the picture of the employees in your company and train a classifier, for instance. Okay, so you take all those images, and for instance, this guy you will try to say this is the employee number something. Okay, so you know how to do that. That's very simple, right? So that's a possibility, but is it actually a good idea to resolve that problem that matter? Well, actually, that's not something that will work very well, unfortunately. Except if you have very large database or if you use basically like very specific techniques. But the main problem is that imagine you have a new employee in the company, and what can you do here? You will have to retrain your entire network for that specific problem. So this is not something very scalable, and it's not going to work very well in the long term. So your boss can be relatively angry at you, and because it's not working, but thankfully you can apply similarity learning to address that problem. So here, what we want to address is not directly to say, well, this image corresponds to that person. What we want to resolve instead is like, is it the same person between like two images? And that's, I would say, like another way we design the problem. So what we want is a network that basically takes two images, for instance, and will tell me what is the similarity between both. And you can set a threshold, and basically if this distance is like superior to this threshold, you can say, well, you're probably different persons. Okay? So that's again like a different way to represent your problem. So for instance, if now the similarity is lower than a certain threshold, then this is probably the same person. So in order to achieve that type of application, like what you can do is use what we call the Siamese network, where instead of training a single network, you will actually train two networks which shares basically the same weights, and you will, like given for instance two images, extract some embeddings from both of these images, and just representative vector for each of those two images. And what you want to do is basically you will compare those images, you will compute the distance in the latent space, like of those two representations, and if your data set, those two persons are different, what you want to do is to basically like have some descriptors which are more discriminated. You want to basically increase the distance in the latent space between those two people. Okay? So you will have basically to adjust the weight of your network such that the extracted descriptor for those two images are spread like apart in the latent space. Okay, so here is an example. So if you have like the same person input and you will extract the descriptor for those two images, you want in that case, because they are the same people, like the anchor image and here you basically have the positive example, you want your network to be able to extract some picture which are the most similar as possible. Okay, so you want them to be closer in your latent space. And if they're like basically two different persons, you want to increase the distance between them. Okay? So it seems like an easy enough problem, but in practice you cannot really do that because imagine if you have like plenty of images and every time you need to basically you will do a path propagation that will reset the weight accordingly, right? And you cannot keep like separating those actually sample apart. You will use you will use all your energy somehow to basically like pull them apart. So what you want to do is to set a certain threshold that we'll call M here, okay? And to say basically, well, if those two samples, like in the latent space, your distance M, okay, I don't really need to push it forward, okay? Like I can just assume I don't want a gradient to propagate through that, and I have done my job, and this is actually enough, okay? So this is basically what we call the edge loss here. So if the distance between like those two samples is superior to M, then in that case we just basically stop propagating and we consider an error of 0. And we can put all those things together in a single equation that you can see here. Okay? Where actually this is what we say, like if it's a positive case, we want to minimize this distance between them. And if it's a negative pair, we want to basically push them apart, except if this distance is superior to m. So, well, I think this is the time now. Okay, we will have a break and we can pursue after this. Thank you. Okay, so basically to address the capture robot problem in our environment. Yeah. So I definitely those approaches that I briefly described can be used. Like again, they're always like everything we have seen so far. They're like just like the fundamentals. Like they don't represent what is necessarily done in the literature, even though they would be strongly inspired by everything we have seen before here. Okay, like NetFlood is one of them. PostNet as well, definitely. It's probably some stuff you came across already. Like if you are addressing those type of problems. And you also use only images for that. Okay, yes. And I think like one of the key for like what will come in the future for those topics is like the multimodal like problem. I would say how you fuse information from different sensors to basically localize like a robot, for instance, in space. Like here I'm just talking about images, but you have to keep in mind that this is often not enough if you want to like work in any possible scenarios, and if you want to localize a robot or a car like in every possible cases, because image like for instance like texture, and you want to combine it, I don't know, with LiDAR or other type of intelligence. Okay, I will continue like on this like contrastive learning, where we have seen that the overall idea was to basically train Siamese network to instead of just doing classification, to learn basically some image representation, some features, such that like similar feature or like similar like image of a person, for instance, or a similar place in our case, will basically be like closer to each other, and like images which are different, that represent a different place or different person, or pulled apart, okay, and at least to distance m, that basically that you will set manually. Okay. So even though you can see that you need here to set like this threshold m by yourself, like this is a bit empirical, right? You can put, I don't know, like any value you want, but keep in mind that actually your network won't be very sensitive to that, because you will just reshape your latent space accordingly, right? So even though that's something you have to set empirically, like normally, like you have this flexibility that it shouldn't affect like a lot what you're doing. So yeah, so we have seen that you have two different type of loss when you have like images which are similar or images which are different. Okay. So in the case of like different images, we have seen that we don't want to basically waste our energy to separate those images to infinity. Okay, like we want basically like if they're far enough apart, given a certain threshold, we will just put r equal to 0, such that we don't waste our time. And we can represent basically those two losses together in a unified manner, like through a single equation. Okay, here is really just by simplicity, I would say. Like by setting parameter y, for instance, that will take a value 0 or 1 if, for instance, like your this is just a flag, right? So if your images are, for instance, similar, okay, you will set y to 1, which will cancel out all this part of the equation, and you will just try to minimize the distance between the images. But if you set basically y to 0, then in that case you will end up in that scenario where you want to maximize the distance between the images, except if they're far enough apart. Okay? So here is what we call the hinge loss, basically. Okay? So, or the contrastive loss in that case. So here we have seen like similarity learning using two input images. So also keep in mind that those type of strategies, they are fundamental not only for image retrieval, but also they are widely used for plenty of other applications. Like they are fundamental for many like approaches for self-supervised learning, for instance. If you read like a bit about Moco or like all those recent strategies, they rely on, like I would say, quite similar mechanism. I wish you can really understand basically like this part well, because because they find sort of applicability for plenty of other things. So we can like work with a Siamese network using like pairs of images, but we can go further than this. Like instead of just considering like 2 images, we can instead try to rank 3 different images. Okay, and this is what we call a triplet loss. Like instead of 2 input image, we can have like a triplet network that will input like 3 different images, and that will try to rank them. Okay, like you want, for instance, imagine you have like an anchor image, okay, which is like your reference image, the image A here, okay, for anchor. Okay, you will extract the feature, same as in the Siamese network, and you will also like have a positive sample, which will be basically another instance, another picture, for instance, of your anchor image under different scenario. Okay, like for instance, a person, but in different illumination, for instance, or with some occlusion, with whatever difference you want, but basically the same person or the same place under a different case. And finally, we need a third sample, which is your negative sample. Okay, that and for each of them, you will extract one representative descriptor. But in that case, you don't only want to make like 2 images closer or further. You want now to have the positive sample closer to your anchor image, and you want your negative sample to be as far apart as your anchor. So what you want to enforce is that the distance between the anchor and the positive sample should be smaller than the distance between your anchor and your negative sample. So you can basically rewrite this relationship, okay, in that manner. Like you can basically put back the distance between the anchor and the negative sample on the other side of this inverse sign, and then you will end up basically with this equation. But again, here we will use the same strategy as we did before in the hinge loss, and we will say, well, we basically want to enforce that like with a certain margin, not to be too rigid, basically. Okay, you don't also want to basically push the images like as far apart as possible. You will put a margin to say, well, they are like far apart enough, basically. And you will end up, if you reshape a bit like this equation, as we have done before, with typically like this equation here. Okay. So now we will end up with 3 possible scenarios in that case. We'll end up with some, I think I have some explanation in the next slide, like 3 different scenarios. You have the easy case, where basically the distance between the anchor and the negative sample is superior than the distance between the anchor and the positive sample, plus your margin. So basically, like they're very far apart, they're far enough apart in your latent space, and then you don't necessarily want to push it further. Like it will have the loss of 0, okay, in that situation. You also have the hard negative, where in that case, well, you haven't done a great job because like the distance between the anchor and the negative sample is smaller than the distance between the anchor and the positive sample. So here you really want to improve that part. You really want your network to learn basically your feature such that you resolve those hard negative problems. Okay? So like in that case, yeah, the loss is positive and larger than m. Okay? So here is really what you want to resolve. And you have a third basically case, which are the semi-hard negative, where well here it's a bit in between. Like the distance between the anchor and the positive is not larger than the distance between the anchor and the positive plus your treasure margin m. Okay, so this is not in the easy negative, but this is basically inside of your margin that you have defined before. Okay, so this is a bit of a, let's say, gray area that they're far enough apart, but like still they don't like go over your margin. So basically you will first have like training on a few epoch, and you will look only for the cases where you have some hard negative problems, and you then can retrain your network on those samples to basically have a better representation of your features. So here is a few examples of image retrieval, basically that were trained in that manner. So you have a query image, and basically we can return like the top n images from a data set, for instance. And it exhibits actually a certain robustness. So I don't know if any of you like already used contrastive like learning in a different context. Like, have you ever used it actually? Because that's nowadays a quite common thing. Well, yeah. Like, because self-supervised learning now is like, I mean, has been a trend for quite some time. There are different, like, I would say, philosophy here. You know, you have like more the Lacan, I would say, family, which would be maybe more on the contrastive side, you know, and you have like other people, and it seems to be quite promising also for like mass photoencoder, where actually it's more on the generative side, and like both of them are very interesting. But you should not, I think, like be too polarized on one or another, and always try actually those different strategies if you want to basically work on self-supervised learning strategy. So yeah, that's the reason why I'm asking if any of you is versed into like contrastive learning or self-supervised learning. No, nobody in the audience is into that. Okay. Okay, so now we can come back to I should have put a link to go back to directly to the NetBlad place. Oh, yeah, I stopped the screen sharing because of that. My bad. I will put it back. Okay. As you can see, I prepared like way too much slides, but I will share it with you later, and you can have the possibility to look at each of it. So many of them are actually related to like very basic topic. I think that's because I know we have different level of students here. Like that should give you like some very easy access to basic problem in machine learning. Okay. Almost there. Okay, we were right here. So let me share the screen again. Oh. Okay. So, yeah, so basically, NetBlad is taking advantage of like this triplet loss strategy, because remember that they don't have access actually to fully labeled images. They just know when something is like, for instance, like not at all similar to a core image, and they have potentially positive cases, but they are not always sure if it shares any overlapping, basically, with the core image you're looking for. Okay? And they take advantage of like the fact you can have a certain margin, basically, to determine when an image is not like fully positive or not. Okay, so this is what we call weakly supervised learning. That was at this time very convenient because there had no specific data set that was like fully labeled, I would say. Okay. So here is okay, I won't go into the details of the result they got, but like back in the day it was quite an impressive one because they were actually much more effective than their ancestor, than Vlad, and also like than Battleworld, of course. So, and again, like this strategy, I would say NetBlad is one of the most employed nowadays. Even though that's super old, this is actually outperforming like many like recent strategies that are coming out. And even like the novel techniques, they're often very strongly influenced by basically NetBlad. Or this is often the baseline you would find actually if you want to test the efficiency of the strategy you develop for this. So we will move to something else now, but maybe like some of you have ever used like any retrieval technique as well, or like pose estimation. What were you doing with that?
It was not for images, so I was doing it for text.
For what, sorry?
For text.
For text. Oh, and you use similar techniques? Or
So it was like, yes, similar kind of, but not like retrieval system kind of.
Also, okay, you're also using contrastive learning as well, or?
It was like similarity between many.
Okay, I see. Yeah, that's extremely close indeed. Yeah, and you can also apply very similar things. And I think like always our field have somewhat benefited like from an inspiration from between text and image specifically. I think. So yeah, that's always good to look a bit in all directions. I mean, like yeah, for a good example is of course the transfer network coming from NLP, and I think like DP gave a like very good summary. I think of like how it's now used in vision in a very successful fashion. I think so. That's a very good example of illustration of this. Okay, so now, well, we have seen like before like post regression and sorry. We have seen post regression and we have seen like the strategy of image retrieval. But like both of those techniques, they have their own like pros and cons, I would say. Like we have seen that like post regression, for instance, is not very scalable. I mean, you will face with a problem when you start to work like at city scale, environment, etc. And the image retrieval, the problem it's actually facing is that you don't solve the problem of visual localization. You just tell me what image is the most similar in the database, but you don't tell me exactly what is the 6 degrees of freedom pose of my camera. Okay, so the problem is like still not fully done. So we have seen that image retrieval is actually quite robust. You know, like I didn't show you any like direct comparison between them. Okay, but like you have to trust my word here that image retrieval will be much more robust to illumination changes and everything. You will see actually in the lab that we'll have today, like you will have to put some noise, for instance, on images, and this is like post regression is super sensitive to that. But image retrieval, that's actually like much more robust to like those illumination changes. Like if you use NetBlad, for instance, in day and night condition, it's likely to work pretty well. Okay, except if you have very challenging situations. But I can tell you, like by experience, that this is very robust. So hierarchical method actually they take advantage a bit of those two words. Okay, like you remember place recognition, we look for like the nearest neighbor from in your database, but it doesn't give you, okay, that's just what I say, the 6 degree of freedom localization. Okay? So what we can do instead is to use those two strategies together. So first, imagine you have like a 3D map of the environment, okay, and you have like the possibility to look the closest images, like that looks the most similar in your database. And if you build your data set using, for instance, a structure for motion pipeline, then it means that you will know roughly where this image was located in space, and you can still have access to this original image and to its descriptor as well. So at this point, what you can do is like use this information to basically match your query image with your 3D map. Okay, so just keep in mind something I said at the beginning of this presentation, is that when you create like a map from structure for motion, that's not the same as a 3-point cloud. You have much more information. Like for instance, every point in your map that you have built from SFM will contain the 3D location of 3 points, but also the 2D descriptor for each 3D key points, the visibility list, which is basically like, well, this key point here was visible from like this image and this image and this image and this image. So actually this is like much more informative. Okay, and you can use that information to basically improve the, first you can improve the image retrieval quality. Okay, for instance, imagine you have like, your NetBlad tells you, well, actually compared to query image, like we have this image and this image, which are very like similar to the query image. And then in that case, because they belong to the same visibility list, that's very likely that this retrieval is correct. Okay, so you can really take advantage of like plenty of information like this. But also you can use those descriptors you have computed before to improve the localization of your camera in space. If you have done a little bit of like, if you studied a little bit of 3D computer vision or projective geometry, you know that if you can estimate, if you can know some basically matches between a 3D environment and an image, you can localize this camera very accurately. So here is actually like how hierarchical localization strategy is working. So first you will extract like features from your query image. Okay? So imagine you take this guy, you run just some SIP descriptor or like anything you want, okay, like super point, super glue, okay, and you will basically extract those features. And after you will basically retrieve that image in your database of images that you have used to make this 3D reconstruction. Okay, so maybe you have done this 3D reconstruction using 1,000, 1,000,000 images. It doesn't matter. Okay, you run basically your netplot, for instance, on that, and it will tell you what image in your database is the closest one. And then the only thing that remains to be done is that you can isolate the part of this 3-point cloud that basically belongs to the image you have retrieved. Okay, because we have those correspondences. We know, like, from your image in your database, what points have been triangulated, for instance, out of that image. So now you can match, basically, this 2D descriptor in your 3-point cloud with your query image. And you can run what we call a PNP algorithm on this to estimate the position of your camera. So also, you will find some slide about like PNP algorithm here that I encourage you to have a look if you're not familiar with this, because that's something we use very commonly, I would say, in computer vision in general, whenever you want to estimate the position of a camera in space. Okay. So the most critical part of that pipeline is not the image retrieval problem, because like we have very good tools for that. Like again, like NetBlad is working pretty well. You will also find like other strategies now that are very robust. So the things that I find actually the most challenging here is like the quality of your local feature matching. Okay. So traditional feature descriptor that you might probably have studied in the past, for instance, SIFT or RB, they're very great for different use cases. But when you start to work in very challenging like scenarios like these ones, okay, with different occlusion, like different like illumination conditions, then this is very likely this is not gonna work as intended. Okay, like just if you try with SIFT to match this image with this one, it's not very guaranteed we get anything. Like here I can see like strong scale difference, illumination difference. Probably it's not gonna work well. So if you're a bit like in the field of like correspondences and localization, you probably studied about like key point detector matching, etc. So we'll briefly see about that. I won't spend too much time on that, but because I want also to discuss another topic after. But yeah, basically the idea of like detection and matching is like first to like detect some discriminated key point on both images. So you extract some key point on image 1 and image 2, okay, and then you extract some meaningful descriptor on both of them, and you will basically try to find pairs of correspondence using, again, like a nearest neighbor algorithm. Like you can, for instance, compute the distance between this descriptor against all those ones and take the minimum one. Okay, just to simplify it. That's not exactly what we do, but that's almost this. Okay? So you will try to find some pairwise correspondence. And if you find pairwise correspondences between descriptors, then you can estimate the geometry of your scene, you can estimate the pose of your camera, etc. So for the past, I would say like, I don't know, at least 7 years or 5 years, I would say maybe, like deep learning based key point like detection and description and also matching, they're really taking over compared to like handcrafted descriptor. So I guess like also many of you have experiments with those type of deep learning based detector and descriptor. I want to briefly talk about like one of the most influential of them. That's probably not the best, you know, you have plenty of other one, but I believe it was the most influential in the field for a very long time, and still nowadays. And this is basically Superpoint. It was one of the earliest, again, like, so keep in mind this is maybe not the best you can use, but this is actually a pretty decent baseline. Okay, so the idea of Superpoint is that given an image, it will use a purely convolutional neural network to output two maps. One map that will contain basically the 2D key point location, and another map that will contain the key point descriptors. So this is very simple architecture. Here there is nothing very complicated if we just speak about like the way it has been built. Okay, the difficult part is always this is the training of this branch. So this is a very fast and simple, fully convolutional architecture for simultaneous key point detection and description. So because, okay, here I specify this is simultaneous because in the previous, I would say, pipeline, what we do is like really we separate the key point detection and the feature extraction, okay, for a certain number of reasons. For efficiency, but also because that was, I would say, the most straightforward strategy we found back in the day. But with a deep neural network, of course, everything is a bit different. So, well, purely in terms of architecture, so we have those two branches. Okay, we have one branch for the 2D key point location and one for the descriptor. So what we do in every case is that we have a VGG network, but it can be anything else. Okay? It was just this one in the original paper. And we were basically taking the last convolutional layer and we try to use this, okay, we have one more convolution, sorry for this, to reshape in the original size of the image divided by 8 and the original 8 of the image divided by 8 with 65 channels. So we have something much smaller than the original image, but what we do is that we consider that each basically coordinate in that map here is basically used to determine the position of one potential key point. So we use those 55 channels basically to give a probability that one point in your image, in an 8x8 zone of that image, will basically be a key point. Okay? So 64 of them are used to say, well, there is a high probability there is a point at this location. And there is also a dustbin additionally to that. So you can see that we have no deconvolution. We don't have actually this part for upscaling the image, I would say. So which can result in different type of problem and also more computation. Okay, for instance, you can have the checkerboard effect. You have plenty of things which are associated with that sort of deconvolution. So yeah. Okay, and you have another branch. So again, we take the representation from the VGG, we have another convolution, we have the similar type of reshape. And what we do here is that you have a certain number of channel for this one, which is 256, which will be the size of your descriptor, and you will basically you will use this map later to estimate the descriptor for each point. So in that case, we'll use the location of the key points. And because this image is much smaller, what we do is basically we interpolate linearly through that feature map. And we normalize it, and it will give you your descriptor for any point x, y in your image. Okay? So this is basically the way the architecture is working for the detector and the descriptor. So I would say that the most difficult part of this work it was to train it in the first place. Okay? So again, they use something we have seen before. They will use a Siamese network to basically train a network to learn similar representation, which will be invariant to different illumination, different orientation, etc. Okay, so if you have basically a huge data set of key point matching between plenty of images, then you can train exactly what we have seen before. You can use the inch loss, for instance, to basically learn a representative descriptor map. Okay? So the main issue here is how you get the data to do that, because we don't have a huge data set, for instance, of key point by human. Or you could eventually use some some matching from SIFT, but then we'll start with a certain baseline that is not actually something you want to do. So instead, what they did, they generated some synthetic data set. They took any images basically. Okay, in that case, they started with some synthetic data they have generated, okay, where they can know exactly where the key points are located, and they can basically have a pre-training of that network using this synthetic data. And then after, they basically fine-tune their network using real images where they have applied some homographic transformation on it. Okay, for instance, they move their image in a certain way, okay, and they will basically use those semi-synthetic, I would say, correspondence to train their network to be able to deal with more realistic scenarios. Okay, so they have these like two different stage techniques where they start with fully synthetic data, and after they move towards like some real images, but simply augmented by homography. So here is some results of superpoint, and you can see, for instance, on the bottom right image, a clear difference like between like the density and overall quality. Here is maybe not entirely clear of superpoint compared to like the over existing type of descriptor. Okay. So yeah, superpoint was much faster than what existed before in terms of like learned descriptor and detector. For instance, lift was very complex to train as well and extremely slow. That was very something not applicable. And I think the difference that superpoint made is that they allowed to actually use those type of deep learning key point for real-time applications. So now we have seen the detection. I will very briefly talk about like now the matching of the images. So the way we do the matching is that you detect key points on both images, as we discussed before, and you will extract some local descriptor for each of those key points you have detected. Okay, like for instance, here we have 3 key points we have detected, and we will extract 3 like individual descriptor for each of them. Okay, and here on the image number 2, you will have a certain number of key points, and you will also extract basically a local descriptor for each of them. And then the thing you will do is that you will compute the distance between like each of the descriptor, like one after another. Okay, not necessarily like this here is a brute force technique. Okay, so you will compute like the distance between one descriptor on the left image against all the descriptor on the right image. Okay, and you will take basically the minimum one as the potential match, and we'll apply something that we call the ratio test to avoid to have ambiguous matching here. Okay, so that was one way to address the problem of matching. So the problem with that type of brute force strategy is that this is super slow because you will have a complexity of O m by n if you have like m point on the left image and n point on the right image. Then it's something that can cause problem when you want to move to like real-time matching. So there are other strategy, for instance, using FLAM, which will be based on a KD tree that also you can find more explanation about that in the slide that we share with you. Okay, where you will basically build a binary tree to store the descriptor of one of your images, and then you can try to find the nearest neighbor using the k nearest neighbor strategy. Okay, so here it's going to be much faster. It will be n log m. Okay, as a speed. But the thing is like. Still, it remains very brittle in terms of matching quality because there are many things that we don't consider here. Like we don't consider the global context of an image, okay, and also like something we'll discuss later, but basically, yeah, the relationship or the similarity between the descriptor in a single image and also the similarity between like across images as well. And this is where also like deep learning mixed actually with different like optimization strategy became like very relevant, I would say. And one of the very nice illustration of this was superpoint. That basically resolved many problems compared to those type of heuristic matching like nearest neighbor that we mentioned or the ratio test, for instance. Okay, so now the question is like, can deep learning like come to the rescue for those type of key point matching problems? Okay. Sorry. So basically, here is the entire pipeline when you want to match 2 images. So you have first the detection, the description that we mentioned, the matching, the outlier filtering, and the pose estimation. So here is what we do, for instance, in a traditional pipeline. First, we detect the key point, we extract the descriptors in SIF, RB, or superpoint, for instance. Okay, so you will have another module for basically the matching. So maybe you will use the nearest neighbor search or like something else. Okay, and after you will have to do the filtering. So again, you will have maybe some over ratio test or like some different like classifier that you can learn. They're also very nice work on that aspect. But you can see, and finally you will have the cause estimation. But you can see that this is a lot of different processes, one after another, okay? And what was interesting with superglue is that they solve like many of those problems in a single end-to-end like strategy. Okay, they do context aggregation, which is not something that appears in the traditional pipeline. Okay, that's something that is actually quite new here. So I think that's very interesting to think, you as a human, how you will solve the problem of like image correspondence. Okay, like if I give you those two images, and I tell you, well, okay, I give you this set, I got this image, I give you this set of orange point here and of blue point over there. Okay, like try to match them, and you will be like, well, that's actually extremely simple, and you will be totally right. But now, let's make it a bit more difficult. I hide those images from you, and I just give you those patches. And okay, like tell me like this patch on the top left, to which part it corresponds on the right here. And here, like everything is more complicated, and I think that's a very good illustration, you know, because, well, actually, like the previous matching strategy, the only thing they can see is this, you know, and you as a human, you have trouble to actually solve that problem. So it means that maybe you don't take the right direction. It's not always like this. You cannot always like say, well, a human cannot do it, so my computer cannot do it. Okay, that's not the right way of thinking. But at least in that case, it gives you a sort of understanding or intuition of like what superpoint, like what sort of problem this is actually resolving. So because context does matter a lot. Okay? So if you're only giving this set of patches, that's of course complicated. Okay. Yeah. So as a human, indeed, like you will consider the context. You will consider like the image as its entirety, right? So that's basically what superglue is like trying to resolve. Okay, like instead of considering each point individually, it will also consider basically like it will basically also consider like the entire like difference between the key point of both images, but also the contextual information between the key points in a similar image. So it will basically build this like correlation matrix between the points, basically. So which is actually, if you just look at this, that's not exactly like the entire novelty of that. Like, of course, they will do a soft partial assignment to find the correspondence, but the most important in this strategy was basically to have the ability to include some self-attention and cross-attention between the image using a graph neural network. And the other novelty was also basically to use a differentiable Hungarian algorithm called the Sinkhorn algorithm to basically perform the matching. It's here basically a transportation problem that is fully differentiated. So I will skip a bit this part because I want to discuss more in details about one of my work I have done recently for localization. Because I don't think I will have the time if I don't skip it. So I want to speak about localization of a vehicle in HD map for autonomous driving. So that's a recent work I have been addressing with some of my friends in the Graduate School of Mobility at KAIST, with really fantastic students working there. And so basically, before I introduce you to the concept of HD mapping, I want you to think about like what is important for like a computer vision engineer that wants to help developing a fully autonomous driving vehicle, like something we call level 5 autonomous driving. So you have two major problems to resolve. It's like the perception problem. So the question of what is surrounding me. Okay. So this is the problem of scene understanding. Okay? Like what did I acquire in my sensor? Like, is there any vehicle around me? Where are they located? How far are they from me? Like, well, we have actually plenty of tools that you probably already know to address that problem. Like, for instance, object detection or image segmentation, and much more than this. Okay. So they are essential. Like this information is essential to take decision in the dynamic world where you have plenty of things moving around you. Okay? So, and you have another essential problem, which again is the problem of localization. Like, where am I? Like the only point of an autonomous car is to go from place A to place B safely. Okay? And you as a driver, for instance, you perform that all the time, and you need to know at any time where you're located such that you know where you need to go, right? So you need the localization in a global referential, or maybe like not necessarily global, but at least in the map or whatever. Okay, you need a referential to know where you are to basically determine where you should go next. Okay, so this is a very essential problem. And again, like you may wonder, well, we have the GPS, and I already mentioned before in that talk, like what are the limitation of this, and that is probably not sufficient basically to perform proper localization for autonomous driving. So there is like something that you might have heard about if you're a bit into like autonomous driving, and this is basically what we call HD map. Okay, so what most of the car companies like they were thinking about, because they all know the limitation of GPS, they all know this is very difficult to build an autonomous car only based on, for instance, GPS information. I mean, if you go through a tunnel, you don't want to be blind. Okay? You want to know where you're located still. And then they were trying to find solution on how you can use perception sensors, not only cameras. It can be LiDAR, it can be anything you want. But how we use a perception sensor to provide an accurate global localization of your vehicle. And it came like quite recently under the form of what we call an HD map, which stands for High Definition Map. Okay, so this is basically illustrated here by this image, but we'll see a bit more details later. But what can you see here? You can see that we have a clear like representation of the different like road markings on the ground, okay, and also like the poles, for instance, traffic signs. So this is basically an HD map. This is I would say a quite accurate localization of the different road elements, okay, which is often represented as a set of vectors. So we'll see that a bit more into details here. So basically an HD map goes a bit beyond what I just told you. Okay? What I described to you was the geometric and semantic layers of HD map. So basically the localization of the different road elements, like for instance the lanes, maybe the road markings, like anything that will build your road infrastructure, basically. Okay. So the geometry part is of course their location in space. Okay. Like something ideally extremely accurate. Like scientific localization is often a requirement for companies building those type of maps. Okay. And the semantic label is, for instance, well, what type of lane this thing is. Okay. Can I, for instance, overtake with that lane, or like what type of road marking is this? Is it like just a straight arrow or a turning arrow? Those type of things. But you of course have different layers that we won't use in the work that we present, but that are still very interesting. Like the lane network is like, for instance, the different interactions between the different lanes. Okay, what action they can perform one another, like can they merge or not, for instance. You have the experimental layer, which is basically more a statistical analysis of different parts of the road. Okay, like at this time of the day, is the road very busy, or is there a lot of accidents in this road, for instance? And finally, you have the real-time HD map, and here is like, for now, just more like fantasy, because there is no company or services really providing that yet. Is that to have real-time feedback, for instance, from the users that will tell you, well, there is an accident in this map and where it is located, or is there any change in this map that occurred? And then you can basically update all the maps. Okay? So, but here for now, we are not at this stage, and like in this talk at least, I will just consider the two first layers, the geometric and semantic layers. So using those type of map has many advantages, and that's the reason why like many companies they are so much into it. Like especially Tesla, like they really like they probably lead the games actually in that technology. And not I will talk about another one later that is doing pretty well as well. But the advantage is now we have a map with the static road element. And that's great. I mean those things are never gonna move. So it means they're perfect landmarks if you want to do localization, for instance. But also for plenty of other things, okay? Because they carry a lot of semantic information. They tell you the rules a set of polylines, just a set of vectors. Okay, so it doesn't take much space. You can store an entire city or send it through a network very fast. Okay, and this is also like globally consistent. Like it will basically give you also information about the GPS location or those type of things in a very accurate manner. So now the main problem of this technology, because imagine you want to build a 3D vehicle that relies on those high definition maps. It means that imagine you drive in a place where there is no map available. Then you cannot basically have self-driving. So you need to tell the driver, well, I'm sorry, but here you will have to drive by yourself. Okay? That's not the type of service you want to offer. Okay? So the thing is, like, you want ideally to have a very clear mapping of the entire road infrastructure of the country. So imagine how difficult it can become. Okay? And there are companies that are doing very well in that game, and this is TomTom from Netherlands. Like, they're very good at building HD map. So they have like an army of survey vehicles equipped with very expensive cameras, like differential GPS, LiDAR, like plenty of equipment. So very expensive, and they're driving around the country. Like they went pretty much anywhere in Europe so far, and they're basically creating those HD maps. Okay, so often they use like a scan from this type of vehicle, okay, plus some aerial view in some places as well. And finally, with a lot of human effort and annotation to basically correct their different algorithms, etc. So they use lane segmentation, they use plenty of different techniques. So the problem is that this is very costly. You need very expensive equipment to build this map. It requires a lot of maintenance. Like imagine, all of a sudden you change one of the road and then you need to build it again from scratch. Okay, and this is also very time consuming. Okay, so this is also very difficult to think of a scalable future for this type of strategy. Okay, so many roads can be unmapped as well. So there are a lot of limitations. And so one solution that many people are exploring these days, I can see DP is a very good actor in this game. I think he worked a bit on HD map, right?
Yes.
Yeah, I've seen 2-3 papers, and yeah, that's pretty good. They try to basically create HD map from cameras mounted on vehicles. Okay, so without the need of very expensive or specific equipment. Imagine you have your Tesla that is driving somewhere, and you can create this HD map and share it on the cloud and improve the already existing map, for instance, or update it in a way. So to basically simplify the maintenance of this very costly map that you create. Okay. So this is actually not really a new problem. Many people tried to address that thing for a long time. I would say the first attempt, they were just trying to do a road element segmentation and applying an homography to put back in a top-down view, and well, that's all. But the thing is, if you do that, you have tons of perspective distortion. That's actually not working very well. It's not very accurate and probably not very useful in many cases. Okay, so people came up with, I would say quite recently, I don't know, I would say maybe 3 years, 4 years from now, with different philosophy here. Quite straightforward, quite simple, but very effective. Imagine you have a vehicle equipped with 6 cameras here to see all around you. So the idea here is to have a neural network that will do the segmentation, but not in the image space, but directly in the bird eye view space. Okay, so you will get basically those type of results that you can see on the right hand side. Okay, on the extreme right of the ground truth. And in green here, you will have the segmentation from this approach called BEV seg forward. Okay, so it looks like it's not a big modification between this one and this one, but actually your network will learn completely different things because you will put everything from multiple images in a single referential and directly in the bird eye view. So you directly learn what is your final goal here. And those strategy, at least for the first one that came out, it was fully based, it was still a segmentation problem. You can see that what you get in the end, this is a bunch of pixels, and that's a rasterized image. Okay. And the disadvantage of those rasterized images is that they're much bigger, okay? They're just a segmentation. They're also, in general, less, not very accurate, okay? And And they're quite heavy, not very accurate, more difficult to understand, for instance, if you want to do autonomous driving. So I would say that many people these days are moving towards vectorized map representation. So basically, just a bunch of vectors. Okay? So you don't have pixel anymore. You just have like some edges and some vertices that are connected with another, like just a polyline structure basically. And this is exactly the problem we try to resolve in the first place. Okay, like our goal that we try to solve is given like given like basically like a set of images where from your vehicle, we want to generate a bird eye view vector map. Okay? Basically, vectorial representation of your road environment in a bird eye view space. Okay? So we wanted it to be real time and to be fully end-to-end. Okay, no post-processing or whatever. Right? So we wanted also this map to contain semantic and instance like information, segmentation. Okay, for instance, like those green line like belongs to a certain category of lane. Okay, like the red one is basically like the separator, and you have the pedestrian crossing in blue. Okay, we have a certain number of categories and also a certain number of instances. For instance, this pedestrian crossing has a certain instance level, and this one will have a different instance label. So we have basically more information. So you can see that there is something specific about that problem, is that we start with a set of images, okay, and in the end, we basically end up with a bunch of vectors. So you have like the difference of modality of representation between your input and output, which requires you to basically design your architecture accordingly, right? So we actually used some CNN to regress, like, or to estimate, not regress, but yes, to regress. To regress some intermediate representation of your environment, and then we process them through a graph neural network to basically estimate the final output that we desire. So the first part is the detection stage, where basically we will use like a CNN backbone, okay, that will extract some feature for each images in your surrounding view data. Okay, for each of the cameras you have, we extract one feature map. And now we put all of them together. So here there are different things. Okay, we can use simply some the calibration information of those cameras, for instance, or we can use a network to directly learn, I will say, the relationship, the geometric relationship between the camera, to merge every of these maps in a single referential, in a bird eye view. So here is what we call bird eye view feature map. Okay, so you have actually all those features that are all like merged into this representation. And given this feature map, we built like two different CNNs, which have two different goals. And actually here is very similar to what we have seen in SuperPoint, is that first we want to detect some key points, which are like different vertices, different vertex, different vertices. This is our vertex map. So this is just a bunch of points, okay? As you can see here, okay, that will basically tell like that there is a lane in that location and that we need to connect those dots later. And we have another CNN that will compute the edge map, okay? So where we'll get basically this type of representation. So we have the extraction of those two elements, and now what we can do to obtain like our final result is basically to use the local feature extracted by those CNNs, and that we can push in a graph neural network to basically like estimate the relationship between these different like vertices, these different vertices. Sorry, how we connect them and how we build our HD map accordingly. So basically here we also use a self-attention layer, okay, and we also like compute some I would say lifted representation of our descriptor by mixing like the descriptor, like the position of the point, but also like the local patch of their edge map. And actually from those descriptors that we compute through message passing, we can build a seniority matrix through a dot product between the key point we have detected, okay? And then we can estimate how to connect basically all these points together such that we build details here. This is a paper that just got accepted very recently, so I can also give you the reference, but I will directly move to like the result we get. So all of this, okay, I know that real time is not a thing if you use a big graphic card, okay, but I will use that a bit, but we made a method that is at least much faster than the previous strategies. And so you can see the input images on the left here, and on the right you can see like the ground truth that belongs to the test set. And on the right side you can see basically the result we have obtained from our strategy. So still this is a bit like, you know, like flickering, I would say. So we have no temporal consistency like developed here. So that's also something we have to work on, I believe. But you can see that we can recover actually the structure pretty well, despite a very complex environment. If you look at those videos, they contain like numerous occlusions, different scenarios where your markings are not necessarily very visible because of wear, etc. So we tested also in more challenging conditions, like for instance, rainy scenarios, and despite also the soiling that can abandon the cameras, then we can still obtain like those type of results. So of course, like I think the most surprising was the fact it's working pretty well even in the night condition. Okay, so here again, that's some test set that that doesn't belong at all to the training, and then nonetheless is dealing pretty well with those cases. And you can see we have tons of occlusions plus the darkness that makes it very challenging. So after we obtain those results, what we're like wondering about is that, well, it's working like pretty well in difficult condition. Can we actually use this local bird eye view vectorized representation to localize our camera in the city? Because they're super light. And so it's very convenient, and also this seems to be quite invariant to challenging conditions like night or day, because you know those road markings, they're easier to detect than different like than over visual landmarks, for instance. So can we like, given a set of image from like cameras mounting on the car, can we basically estimate a local like road element representation as a set of vector, and then try to compare this with an entire HD map of a city. So the question is, how fast can it be, and how robust actually we can go with only this information. So we had actually a lot of surprise doing this. So the idea is exactly the same as what we have seen before. Like we build first, so we sample like different like local vectorized representation on our huge HD map. Okay, so we do plenty of points randomly, and after we basically train, and you will see later, like an encoder to basically extract one local descriptor for each of the samples. Okay, so exactly what we have seen before in this talk. And then you have your current image. Okay, so a set of vector again, and we apply the exact same encoder, and now we can simply try to retrieve this descriptor in your database to localize basically the position of your car, only based on this like very compact descriptor. So well, like it's still at the early stage, but we realize a certain number of things. Is that if you only rely on those vectorized representations, well, that's not good enough. You can see that here is basically the vector only representation. And okay, those scores, they correspond to like, is in the top one result that my retrieval algorithm gave me, is the top one the correct one? And in only 66% of the cases, we were retrieving the right position. Okay, so in comparison to NetFlat that we have seen before, or to other like strategy based on images, we were much lower than them. But this is actually a very obvious thing, is that if you only look at the road elements, imagine you drive in a pure straight line. Okay? So in that situation, this is very degenerated because you can be at any location on that straight line, and you will have exactly the same representation of your environment. So using only the road marking is obviously like most of the time not enough. Or you will have to basically like accumulate the representation over a certain length. Like you will have to put together multiple images over time. In that case, it would work great. So what we did for now is simply like fusing like those like image descriptor, like NetFlat for instance, with our vectorial representation I presented before. So we basically developed a module using some transfer network to some sort of adaptive, like multimodal fusion between like the image representation and the vectorial representation. So there are still plenty of things to do in HDMap, like about, for instance, for now, what we have done is only using like the static element in the scene. But there are plenty of new works that are also trying to detect like dynamic object in those 3D maps. So here is one example, but this one you can see that is not in a vectorial representation, but still in a rasterized way. And there are still plenty of things to discover and to make it better or more effective. Another problem as well is that most of the time when you train a network on a set of image, like if for instance you swap two of those cameras, then your network will be super lost. Okay? Or if you move the orientation of one of those cameras, then it's not going to work anymore. You will need a full retraining of the network, and this is not very versatile in that sense. So I think like we really need like to push towards this direction because there is a lot of needs for those type of strategy in industry. And in the future, I would like to see if it's possible to basically play with that for more challenging problem like multi-vehicle, like mapping, for instance, how we can combine information from many cars, or inter-car pose estimation using like sharing those type of information. Okay, so I will finish this talk. I don't know how long I have. It's okay, that's great. So I will finish this talk on like a few like trends in localization. So one of the obvious one, this is of course like nerve-based localization. So the video seems to be a bit broken. Ah yes, okay. So actually this thing has been released like I think like last week by Niantic, you know, the company doing like Pokemon Go. And they basically propose a new localization technique inside of implicit nerve representation that works in real time, and apparently that is already in production for more than a year. And that was very impressive work. That shows actually like very like promising direction. You can see as well that you have the scale of the camera error pose, and they have like something very decent. So I don't know exactly how much scalable it can become, but this is actually something interesting. So there are also like I would say like work that try to take more advantage of semantic information in the scene. Okay, for instance, the detection of some window or like semantic elements, such that you can basically that can help to localize your camera in challenging conditions, for instance. Okay, so you can basically guide your localization based on those local like elements. So there are also plenty of new benchmarks. It's very interesting nowadays to basically address new challenges and new problems that comes in the industry, like typically like how you localize someone equipped with the AR headset. Okay, so over an entire building, for instance. So there are like very large data set now about those very specific problems. There is also like a new challenge that seems very interesting is a mapless localization. I think in the first slide of this talk, I told you like, well, we always localize ourselves given a certain referential. Here the idea is not exactly that. I mean, your referential is simply like the single view you take, and after you will try to figure out where you're in space with respect to this image. Image-based like matching and localization, but here is a bit more twisted because you want to be able to keep a correct localization across like a very complex path and across very different viewpoints. So well, that will be all for today. But if you have any questions,
When you say use information from parts, does that mean different car companies have to be on the same systems, or is it only within what's already
Yeah, that's actually a very big problem in the future. Like, indeed, like ideally, like I mean, actually there are already some unified system. What's the name of it? C2PX. Like there is different um, standards that are emerging, especially actually from China, and many companies use those standards. It doesn't mean that like a car company will allow other car company to access it. I would say that that's a very complex problem that goes even beyond that. It's like maybe every car company will equip their vehicle with different sensors, and now you deal with that as well. So yeah, for now this is actually a problem that hasn't been addressed at all, I think, and I don't think anyone wants to yet actually try to resolve that problem because it causes a lot of issue in terms of privacy. And already these connected vehicles, they are like causing a lot of turmoil in the US. Like we have more and more Chinese car companies equipped with plenty of sensors. And like imagine you have like one of those cars driving around some sensitive, I don't know, American Army base, for instance, and they capture images and they use those images to train their network. But like, yeah, the US government is very like, I would say, skeptical about certain the usage of those images. So yeah, your question goes like very very far beyond what I can say, but yeah, that's indeed a very important problem, and maybe it can raise actually new problematic in our field. Like, do we really need image to retrain the network? Can we encrypt them in a way first, like for instance, that can be reused without any privacy problem, etc. And that will potentially like help to share information across different like companies without the fear of like using their data or using like any like customer data or whatever like this. So, yeah, I think there are lots of work in that direction. We're very far from this, and very few people work for the problem of connected car using computer vision on this. So that's still a very emerging problem. Yes.
Why do we take top two matches or top two nearest neighbors specifically in football
When we take the top two, is simply to apply the ratio test. Like we consider that, so we take the two best, and we're like, well, let's see if they are very close one another, or if actually this is discriminant enough to trust them. And if they're too close, those top two matches, then we are like, well, actually we're not very sure which one to assign. Okay, so we're like, well, we'll just drop it. We don't consider this match anymore, and then we give up. So this is what we call the ratio test. That's the reason why. We take it up. Yes.
So could you explain a bit more about localization using NOR?
Oh well, actually this is a new paper. I haven't read it. It came out a few days ago. So here is the reference. Again, I will share everything. I have no idea what they're doing, but it looks super cool. So I will definitely read it. So yeah, I recommend you to have a look. But also you can have a look to if you're interested in that in like. The old one was self-supervised NER. Also, there are new paper from Facebook on those type of localization problems, which are pretty cool as well. So, yeah.
What do you think for like using more percentage sensors, right? Can we use the
So more sensors, like for instance, like merging lidar and cameras. Yeah, I truly believe that sensor fusion is an important thing. And you know, like in the result I have shown you for this HD mapping, thing in the end, like actually people have developed like some sensor fusion strategies, and they work much better, obviously. And I think this is a great way. The problem is more like when you deal with companies' issue, like how much it will cost me. So yeah, doing this with pure images is great. I think you can do much better with multiples of data, but it's always a compromise. Like I think between the cost, like the maintenance and all those things. So yeah, but I believe as probably you do, like in data fusion. Definitely. Okay.
What are other practical applications of feature localization other than like practical applications that can add up to this?
It can also be used like for instance 3D reconstruction. Okay, if you want to incrementally grow a 3D point cloud, for instance, typically, or if you want to speed up reconstruction as well. Okay, so in that context, so not only you can localize yourself, but you can use it to improve like your mostly, for instance, augmented reality, mixed reality, like everything related to heritage as well in that context. So, well, that's mostly related to that, but yeah, also for reconstructing things.
Okay, that seems good. Thank you so much, Professor Doctor. Thank you so much. I'd just like to request the General Chair of Finance 2023, Dr. Suman Rasbas, to come up and hand over a token of love to Professor Dr. Pons. Thank you so much. All right. Okay. We just want to also appreciate our best delegate for today. Brother, what's your name? Yeah. So can you please come up? Go ahead. So, Wanda, could you please come up again just to give him the chocolate award for the day? Okay, thank you so much for being an awesome delegate during our Central Lab session. So guys, as you know, we have the tea and biscuits